I said Martina. I'm gonna buy it.
Hey, John, Ernest. Shut that door for me. All right, got a new assignment sheet.
Oh my gosh, for Friday?
What? That's in March.
Did he not say assignment sheet?
Assignment. Hey, you might go do some crazy.
Why did that?
You got 3 review days, right?
I know. Please tell me there's no sign up sheet for on there.
Oh,
It's like one semester every day.
Wait,
okay.
I'm gonna be thinking about
one
our
semester. Oh, wait, no.
sweet friend community. She's having like an emergency wisdom tooth extraction. That doesn't sound great. Planned wisdom tooth extraction sounds bad enough. Emergency sounds, I don't know, maybe a little painful. No, I'm not. Your old one is garbage. Hey guys, feel free to take your, can't talk over you. Feel free to take your old one, recycle it responsibly or throw it, whatever. The things that have changed are, notice it does not say begin ellipsis and hyperbolas yesterday. It starts today. We'll finish that tomorrow. We'll do a little let's see what you know worksheet to kind of finish it off on Thursday. We'll talk about the pesky XY term, which will be new to all of you, and what that does to a conic. We're going to do a little Q&A on Monday. I'm thinking, unless I change my mind on Friday and say, you know what, let's just go ahead and knock this test out Tuesday, but probably this is the plan. And then probably the conics game on that Tuesday. So we'll test Wednesday. You'll still have a 3-day review, which again, I think is fine. You guys are the first exam though, so keep that in mind that you will not have to be able to drag it on like other people, which in some ways is probably nice.
Yeah.
Again, if I were you, I'd really be working on this review sheet. If your average is one of those where you're not going to have a big cushion, so if you have a really low B and you want to hang on, I would not wait till the last second. If you have a really high C, you can totally bring it up to a B, but I would really, really be working on this review sheet to make sure you can go through it all, do it all, correct it all, and still have a chance to go back and redo the stuff you missed. If you don't do this review sheet, because I'm not taking it up for points, I may take it up, but I'm not taking it up for points. And I might do that just to take a look. So if a parent goes, what happened to sweet Johnny? But what happened to sweet whatever Pierre? And I can go, well, sweet Pierre. Oh, dang. Pierre. No. But I can always say, well, they didn't really do the review sheet, so it stands to reason they would get hammered. So, but if you do that, most people who study and prepare well do well and exceed their average. The people that don't exceed their average, honestly, are the people who either A, don't do anything and just pray it'll all work out, or 2, the people who just don't need to do well. Like, I know that there's somebody in here with a 98 semester average, and if you do the math on that, hey, if you do the math on that, you're looking at like a 57 you need to keep your A. Well, if that's the case, I got to be honest, I don't know that I would be killing it. If I knew 98% of it going in, I'm pretty confident I'm going to know 57%, probably right this minute. I'm not saying to roll the dice on that. It would be a horrible shame for that to happen, but I have not seen that happen in the past. So somebody lose a grade like that. But those are the people that tend to make high C's when they have A averages. It's the ones that can afford. All right. So anyway, prepare well, and I think you'll be okay. And this conic stuff is the last thing that will be on there. So we left off with, I think we got through the majority of ellipses and with parabolas and circles, but it seems like we did not talk about, what page are we on this? 85. Okay, so one thing we did not talk about on parabolas is what to do when your a value is not a fraction. Now we said when your a value is a fraction, and I'm saying fraction loosely, when your a value is between -1 and 1, which for the most part is something like 1/4 or 1/8 or 1/12 or 1/20, something like that. But when it's in between -1 and 1, I find the lattice rectum, and I find that by doing the reciprocal of a, making it positive because it's a length. And so I find that length, right? And actually, we looked up lattice and lattice latero. I'm a little sketchy on my Latin as well. Latero meant width. Lattice actually means side, which actually makes sense that the lattice rectum would be the opening from side to side. So that still makes a little bit of sense, but stands to reason my 1982 Latin skills are a little shaky. But anyway, and then I went and took the lattice rectum and did what to it to find the C value? Divide it by 4, took 1/4 of it. That gives me the C value, and the C value is my distance from the vertex to the focus, right? So I find that distance, and as long as I know which way it's going, I can just mark that distance, stretch out my lattice rectum, and I've got those 2 points, the vertex, to sketch a parabola. And as long as I know which way it's going, which I should know, because if the y comes first, it's up or down, opens up or down. And if the x comes first, it's opening right or left. The sign of the A determines the direction. So with that, coupled with your C value and your lattice rectum, I should be able to get a good sketch. And if I didn't mention this yesterday, there's also something called the directrix, which we really didn't mention. The directrix is this line. It might be horizontal. It's horizontal when it opens up and down. It's vertical when it opens right or left. But the directrix is also COA. And it's this line, and a lot of people look at it and they go, why do I even need that? Well, the real definition, not the slice through the cone definition, but the real definition of a parabola is this. It's all the points. You know how the definition of a circle is all the points in the plane that are equidistant from a fixed point called the center, right? Well, the definition of a parabola is all the points in the plane that are the same distance from a focus. And we see the focus right there, right? So everything that's the same distance from this focus as it is from this line. So if you think about what that means, the same distance from the focus as it is from the line, well, the vertex is the same distance from that as it is to that. Over here, that right, let me use it better. Okay, so that point right there is the same distance from there as it is from there. That point there, same distance there, same distance there. That, same distance as that, and that. That, same distance as that. So if I were to take all the points that are the same distance from the focus as they are to there and connect them all, that's what makes a parabola. But do I need the directrix to help me graph it? Not unless you want to graph it this way, and I don't. So what I do is I just use that C value to mark the focus, and then I use the lattice rectum to stretch out that length, and that gives me that point, and that point. And if I know it's a parabola, I can kind of wing it and just sketch something in there, and that's good enough for government work, which is ironic, really, because government has so many regulations. It's so much harder to do everything with government, but whatever. But we'll let the old saying slide. Are y'all with me with this? Now, the one thing I did not talk about is what happens when your A value is not a number between -1 and 1. See, that kind of blows up a little bit. So let me just give you an example. I'm going to go grab a graph. Okay, so let's just say that I have this parabola here. So let's just say I had something like y plus 4, and let's just say I had positive 5, and then x, how about +2 quantity squared? So what you should be able to see on this is, first of all, it's a y. that leads off that's not squared. So what do you know about direction? It's either going up or down, but you know it's going up because the A is positive. So I already know that it's doing this. So I know that the vertex is located at -2, -4. So -2, -4. So I'm going to go left 2, down 4. There's my vertex. Okay, so I know that, and I know it's going up. Well, the problem with using the lattice rectum here is the lattice rectum would have a length of what? 1/5. So literally the opening of the parabola is 1/5 wide. If this is 1/5 is like some small little amount. Now, how far is the focus from the vertex? That's C, right? What's C? 1/4 of that, which is 1/20. So literally, I am asking you to right here go up 1/20 and then have a width of 1/5, which would be literally 1/10 to the right, 1/10 to the left. All right, sketch your parabola. See, it just doesn't work well, does it? So what I'm going to do is I'm going to go back to thinking about just an ordinary stretch. And if I think about a regular parabola graphs how? If you knew the vertex. Plug in a 1, go up 1. Plug in a -1, go up 1. Plug in a 2, go up what? 4. Plug in a -2, go up 4. That's what a regular one would do, right? And you have the 2 points and the vertex, and you connect the dots. Well, if I put a 5 in there, like I have a 5 in here, instead of plugging in a 1 and going up 1, what does the 5 do? It multiplies it by 5. So really what I'm doing is instead of going over 1, up 1, I'm going over 1, up 5, and then left 1, up 5. So it's almost like I'm treating that 5 like a slope. It's like I'm going up 5 over 1, up 5 over 1. Now, can I keep doing that? If I could keep going up 5 over 1, up 5 over 1, up 5 over 1, what would I have? I'd have an absolute value, wouldn't I? So I call this my cheat trick, all right? And don't go and say that in college or anything. It's a cheat trick because it's not worth very much. But what I'm saying, and I'm naming it after the 70s rock band. Anyway. So does anybody know cheat trick?
We talked about it last year.
Okay. So the cheat trick is when your value is not between -1 and 1, and it's something like 2 or 4 or 7, then ignore. You can still find the lattice rectum in the C value. You can still do that, but I wouldn't use that to graph it because it's not helping. So what I'm going to do is once I find that vertex, ignore that right there. But once I find the vertex, I'm going to go, oh, the A value is 5. I'm going to go 1, 2, 3, 4, 5, 1, 5, -1, and I'm only going to do it once. I can't go again like that because remember, 1, 5, 2 would have been up what? 20, because 5 times that 4. But it won't matter because you're off the graph, right? Because remember, if I plug a 1 in, I get 1. If I plug a 2 in, I get 2 squared is 4. So if I had to multiply, because 2 squared is 4, times 5 would be 20. Well, I'm never going to get a chance to graph that. So again, all I need is a couple of points. So use the cheat trick, which is basically go your A value over 1. Just so go up over 1 each way, and then just sketch your parabola given that. Are y'all seeing that? So that's what I would do on the cheat trick. Now, when it comes to actually answering questions about a graph, let's just say, I know there's one in here somewhere. Maybe on the next page, review 2. Somewhere. Really? Maybe not. There's got to be a review here, right? Nope. Oh, well.
You don't have to know that.
No, you have to know it. So hopefully you just took a couple notes. Anyway, let me get back. Yeah, just make sure you know it. But use that cheat trick to actually go up, over when you're value. And if it's an X first, like right here, hypothetically, on this problem right here, and I guess you don't need to do that because there's a 112. But like if that had not been a 112, right? Maybe instead that was a negative 4. So let's just say there was a negative 4 was your A value. You can still go 3, 1, 3, 1 for your vertex, right? Which way is this graph going? It's going left because it's X and because the A is negative. The 4 is not between negative 1 and 1. So instead of going up 4 over 1, what do you think I'm going to do? So I'm going to go left 4 and then up and down 1. And then that's enough for me to sketch my parabola, except this one's more than just a parabola. It's a what? It's an inequality. So I can sketch the parabola in there. It doesn't have to be dotted because there isn't equal. But how would I decide where I shade? I can pick something inside that or outside that to check, right? Don't pick the vertex because the vertex is on the curve. Are you with me? I can pick centers because they're inside the curve, right? They're not actually on the curve, but a vertex is on it. So don't pick it. Pick something like maybe 0, 1. Pick that right there. If I plug a 0 in there and I plug a 1 in there, what do I get? 0. Is that a true statement? No, then shade everywhere else. Y'all seeing that? And when it comes to answering questions, this is where this gets a little tricky. I can look at this and really clearly tell that my vertex is 3, 1, right? How do I tell what my focus is?
The C value over.
Okay, let's think about this. I don't have to graph it. It says label it, but it's going to be really hard to label your focus right in here. Well, remember I gave you a different number. So I wouldn't ask you to label a focus if it was negative 4, right? But if I did ask you what the focus was, think about it. What do you do to find the focus? I have to find the latus rectum, which would be what? 1/4. Then I'd have to find the C value, which is 1/4 of that. And what way would I go to mark the focus? I would go left. So how do I go left 1/16 from that? Do y'all see that you would subtract 1/16 from that x coordinate? Do you? The y is still going to be 1. So I don't want to mess with that y. But I'm just going to take that 3. And if I go left with it, I subtract 1/16 from it and then just clean it up. So 47/16, I guess, or 2 and 15/16, something like that. And that's my actual focus. Are y'all seeing that? And if I said, what's the directrix? Where would the directrix have been? The line just to the right of the vertex, right? So what would I do to find the directrix?
1/16 plus
I'd add 1/16 to the what?
X value.
To the x value, but it's not a point. It's a what?
Line.
It's a line. What kind of a line?
Dash.
Vertical. So x equals. So I get x equal 49/16. We're going to do this little thinking more when we can't graph something, but we still need to find its value. We'll do this more with ellipses and hyperbolas in a couple seconds. Are y'all kind of seeing that though? So you might be asked, but remember, a directrix is a line, a vertex and a focus are points, and you have to label them like that. And when you get weird values that don't really make sense, you can still find them, by adding or subtracting. And if this graph was going up, what would I have added 1/16 to? I would add it to the y coordinate. If it was going down and I'm trying to find the focus, I would have to subtract it from the y coordinate. Are y'all kind of seeing that? And that could be tricky for some, but that will be an element of this test. So at this point, you should be able to have a fighting shot at doing the problems with circles and parabolas if you want to look through there and see those. But you can also see that I'm not even making all your reviews done. It says begin review, work more on them tonight, and then at some point get them all done. I actually forgot to put that on there, but get them all finished for your sake by the end of the test day.
Are there more than just these?
Well, there's the random miscellaneous conic stuff. There's the let's see what you know. And then there's the conic sections practice stuff, the stadia stuff. So there's other stuff out there. Okay, so let's go back to ellipses and hyperbolas. So I want to talk about ellipses and hyperbolas simultaneously. Okay, so it might be better. Well, I tell you what, we've already done ellipses and hyperbolas, so maybe I don't need to do that. So let me just walk you through ellipses and hyperbolas. First of all, if it's an ellipse, when you are looking at its form like this right here, how can I look at that and tell it's an ellipse and it's not any of the other ones? And again, if you forget this,
Big numbers.
I can tell because there's a little note down there at the bottom that says, how do you know if an equation is ellipse? So how do I tell?
Different coefficients
So you have different coefficients, but there's more than that
from square variables.
with the same sign. If I have different coefficients with the same sign, it's an ellipse. If I have the same coefficients with the same sign, it's a circle. And if I don't have two squares, it's a hyperbola. And the only other option is what happens when x squared and y squared don't have the same sign, whether they're the same coefficient or not. If the signs are different, those are hyperbolas. Okay, so I look up here and I see x squared and 25 and they have the same sign. So if it's going to be any of the conic sections, because they have the same sign but different coefficients, I know that this must be an ellipse, but it's still possible that it's a degenerate ellipse if I end up with a 0, or that it doesn't exist if it ends up with a negative. So you got to remember that. And by the way, for the record, those would also be points along with circles. Ellipses and circles are related kind of like rectangles and squares. A square is a very specific kind of rectangle, right? Meets all the conditions of a rectangle, but the sides are the same. Well, a circle meets all the conditions of an ellipse, except you're going to see that your summifocal radii, or whatever, we call that a radius instead of a summifocal radii, and your foci come together, and there's all kinds of little things. But anyway, that's neither here nor there. So let's take a look at these. If I can get it into this form, then what can I deduce from this? And you'll notice with this form, I've completed the square with the x and the y. There is no coefficient in front of my parentheses, but there's numbers on the bottom. And I have to look at the numbers on the bottom, even if they're not perfect squares, and think of them as perfect squares. So like if I had on the bottom here a 36, then my A might be 6. If I had a 49, my B might be 7. Okay, and it's important to know which one's A and which one's B, which we'll talk about in a second. If the number was like 10, well, now my A value is root 10. Or if the number is 12, it's 2 root 3 or root 12. All right, so whatever number's down there, when I square root it, that gives me this A and B value that I'm going to need to graph. Okay, and then it always has to be equal to 1. If it's not equal to 1, make it equal to 1 by dividing everything by whatever that number is. Now, you'll see that when I complete the square. Check it out. Right here. If I gave you this, I take a look at it and I go, oh, look, 2 squares, different numbers, both positive. It's got to be an ellipse unless it's something weird, degenerate or something. So let's see what we can do. So like I did with the circle, the one thing I'm not going to do is I can't divide through by the same number there because it's not the same number. So instead of dividing it out, what I do is I put all of the x squared terms together. So you'll see me blush. I put my x squared terms together here and my y squared terms together there. And I just move my constant and get it out of the way. Right? And then because I can't divide everything by one number and get rid of both of those without creating an ugly denominator, what I do is factor out that lead number on both of them. So I factor out a 16 and I get this, and I factor out a 25 and I get that. Then I complete the square. Okay, so when I go to complete the square here, I'm going to go half of 6 is 3, square it's 9, but did I really add 9? No, I added a 9 inside the parentheses, but you can see if I were to distribute it out, what I really added was a what? 144. And then here to complete the square, half of 4 is 2, square it's 4. But did I really add 4? If I FOIL it out, I really added 100, right? So these values right here, that 9 and that 4, when I put them in there, you got to remember that you're really not adding 9 and 4 to both sides. You're adding that and that to both sides. And then I do the process, right? Drop the 16 down. We know how to factor perfect square trinomials, right? Square root of the x, square root of the 9, sine of the middle squared. Square root of the y, square root of the 4, sine of the middle squared. Drop the 25 and the 16, add all that stuff up. And now I look at this and it looks a lot like a circle. In fact, it would be a circle if those two numbers match, because I would, like, if those were both 16s, I'd divide by a 16 and have a circle. But with an ellipse, they don't match. So what I want to do is make this number 400 equal to 1. And I do that by just dividing by itself everywhere. And in a perfect world, that's going to give you 1. But in a perfect world, everything's going to cancel there and give you nice, pretty numbers. Now, what happens if it doesn't cancel nice and pretty? Like, what if, I don't know, what if this number right here was 15? Right? And 15 doesn't divide nice and evenly into that. Now, you might try, like, what if I divided the 5 out and I got 3 over 80? Well, in that rare case, don't leave the 3 there, because that's not my a squared term or my b squared term, whatever. It's not. I have to make it that, but I'm not allowed to have a 3 there. So anybody know what I do with that 3? I put it under the 80. Because think about it. If I put it under the 80, isn't dividing by an 80/3 the same thing as multiplying by a 3 over 80? So I just take that 3, swing it under there, and then that would be my a squared term. Most of the time, if I want you to do anything with this or graph it, I will make these numbers nice and pretty like you see.
Very pretty.
Like we see.
Nope, that's not what I wanted.
Do you have the graphing string for the ellipse that we did last year?
Oh, yeah.
You guys
So
are
it's
right
there.
there.
The fame graphic.
If y'all paid attention.
Come on, really? There we go.
Hey.
So at this point, I divide by 400, cancel, and then here's where I'm going to be able to tell all my information from. Now, one thing it's important to notice, and you're going to do this exact same process if it's a hyperbola. The only difference is when you're done, you won't have pluses in front of each term. That's technically a plus. You'll have a plus on one and a minus on the other. And if it's me, if the minus shows up in the front, I just switch those at that point. Okay, and sometimes it does do that because sometimes this number is negative. Now, by the way, what happens if this 400 is a 0? It's a degenerate ellipse, which again, remember, slices that make ellipses are slices through here, right? They make ellipses. But if my slice goes through the tip, it still makes a point, right? So just like a circle's slice right there, horizontally, if it has a slight slant, but it still hits the tip, it's still a point. So it would still be a point, a degenerate ellipse, which makes sense because it's in the same family as a circle, right? Ellipses and circles. Now, if it's a negative right there, then that doesn't make sense, does it? Can you square two things, add them together, and get a negative number? Not unless they're imaginaries, and we don't have imaginaries because they don't graph, right? So if you end up with a negative over there, I'd probably double check your math and make sure you didn't make a careless error. But if you do end up with a negative, you got to go, wait a minute, this just doesn't exist. Because if I divide through by a negative, having a negative there and a negative there is not a function that we know. Right? So you would just go, all right, this, whatever this is, doesn't exist. Now, at this point, I need to talk about the actual ellipse and what parts of it mean. So if you go back to what we know about ellipses, and I'm going to go back and look at this picture of one, okay? So if you're looking at the picture of the ellipse, this is the actual graph of that ellipse. It has a couple little characteristics that you need to know. The first is the longest length we call the major axis. The length of the major axis is like from the long end to the long end. And there's got to be a longer end because if it's the same there as there, it's a circle, right? So if it's stretched either here or here, the longest is the major axis, and the major axis is always 2a. Okay? Now, the a value right here is the amount, it's the biggest of the two values that are in the denominators up there. One of them is an a, one of them is a b, or technically one of them is an a squared, one of them is a b squared. The biggest of those two is the a squared. So when I square root both of them, the biggest value is the a, the smallest value is the b. Okay? But on these right here, you'll notice that the a always moves in the direction of the variable that it's under. So when you look at this, back to this picture, come on, right here. If I have a 25 under x, the 5 is under the x, the 5 is the a, and it moves in the x direction because it's under the x. The 4 is under the y, the 4 squared. So the 4 is the amount that you move in the y direction because it's under the y. That part is true also on ellipses. And that's really all you need to graph it. So if I know the center, which is 3, -2, and I mark it, and then I go, all right, 5 squared is under x, 5, 5, 4 squared into the y, 4, 4. I've got 4 points. I can kind of sketch an oval out of that. And if you struggle with your ovals, again, little parentheses tend to help kind of get you a decent graph. Okay? Now, so that right there is my a squared. That's my b squared. So my a ends up being 5. My b ends up being 4. Now, there are foci. Instead of focus, there's plural. You could say foci or foci, just whatever. The foci, the two focuses of the graph, they are in the inside of this ellipse. They are to the right and to the left. And if you remember that little string thing I did last year, where I put the string in there and then sketched out an ellipse, remember that? I guess I still have that, but I sketched it out. Those foci are what generate an ellipse in the real definition. But we're not going to actually pull string out and do that on our test, okay? So what we're going to do is figure out where the foci are located. Based on our picture, you can see that each focus is how far away from the center. You can see that it's C away. Dadgummit. Man, this thing is struggling, or I'm struggling. Okay, so you can see that my C value right there is the distance from the center to the focus. It's also the focus that way. Now, if you're wondering where the foci left and right, or are they up and down? Depends on which way it's stretched. If it's stretched more this way, but they always lie on the major axis, right? So if it's stretched more this way, put C there. But your C value is different from your old C value. There is a lattice rectum here, but it doesn't work the same way. So what you got to know about this is the relationship between your A and your B. Why won't that go away? Between your A, B, and your C. So let me show you that relationship, and I wrote it up here. Instead of a squared plus b squared equals c squared, like you learned on the Pythagorean theorem, it's a squared equals b squared plus c squared. But I like doing it a little bit easier way. Here's what I do. Instead of memorizing that, I know that c squared is always that opposite sign, that a squared minus b squared. And then when you get to a hyperbola, when there's a minus there, you're going to go c squared equals a squared opposite sign. You're going to put a plus and then b squared. So it's always c squared equals that opposite sign of that. And if you just remember that, you're in great shape. And that's a great, easy way to find c. And you can look at these and see that that's really the same thing. And that makes it where you can actually do it in your head. Like, look at this right here. I can look right here and go, all right, my c squared is 25. That's the a squared minus the 16. So my c squared is 9. So c is 3. So I should be able to do that real quickly. And if we have our review game, bank on that being a question. All right. And then once I find the c, I know how far the foci are away. So I can take the center and I could go, all right, 3 to the right means I add 3 to that. And I get 6, -2. And did I even write that on here? No, I didn't. Why I didn't, I have no idea. So if I was actually trying to find the actual each focus right here, if I was trying to do that, I take the center, which is 3, and I add 3, -2 to get 6, -2. And then I would take the 3 and I would subtract 3 to get 0, -2, right? So plus or minus, and those would be the location of the two foci, and you can look down at your graph and see this. Are y'all with me on that? Okay. Now, there's also vertices. Vertices, these things aren't technically super needed, but it's a question that could be asked. The vertices are at the endpoints right there and there of the major axis. All these points are on the major, right? The vertex is how far from C, if it's all the way to the end. A. So all I would have to do to find my vertices is go back to the center, which we already said was 3, -2. And I'm going to add and subtract the A value, which we know is 5. So if I want to find the vertices, I'm going to have 8, -2, which you can see right there. and I'm also going to have -2, which you can see right there. Okay? So you need to be able to find the foci, the vertices, and those are all on the major axis, whether the major axis is going this way or this way. Now, there is a minor axis. The minor axis, since that was B and that was B, is just 2B, but we don't have any special names for points on those. So these aren't also vertices. Vertices are only on the ends of the major. Okay? And then the last thing, if you remember this little thing I did with the string, the sum of the focal radii right there, that sum is always equal to the length of the major axis. It just is. So the sum of the focal radii, and by the way, the definition of an ellipse is, hey, if your sum of focal radii is constant, what that means is focus to graph, graph to focus. The sum of those two lengths is always the same thing. And that's what we did with that string. We, like if you think about it, we like plot some string down and we said, oh, this is going to be all over the place. But we kind of traced our ellipse. Oh yeah, that's not going to do well at all. But anyway, we traced our, good night. Still going.
It's got a mind of its own.
Isn't that crazy? Anyway, but anyway, right here, the sum of focal radii, the string doesn't change length right there. So if the string, yeah, that's a terrible idea. So if the string doesn't change length on this thing, then the string doesn't change length, then these points on here are just a result of that string being stretched. And if I take that string and I stretch it out to the endpoints, it happens to be the length of the major axis, which is also 2a. So remember that the sum of the focal radii and the major axis both have lengths of 2a, but I wrote that up here, I'm pretty sure. Maybe I didn't. Yeah, sum of focal radii is 2a, length of the major axis is 2a. Lots of that. And again, if a is always the biggest number, which it is, a is always the biggest, then all I got to do is look at a ellipse and go, oh, well, that a squared must have been 25 because it's bigger, so a is 5, b must have been 4, and I'm on my way. Are you seeing that? So you're going to have to know how to graph these, know how to complete the square. There's also a couple of other things like the length of the lattice rectum. What was the lattice rectum on a parabola? It was the what? It was from one side to the other side through what? Through the focus. This has that too. There's a length from one side right here, from one side to the other side through the focus. And it happens to be the same whether I go over here or over here. Well, I used to make people do this the hard way. And the hard way is find the value of the focus, the x coordinate, find that, shove it into your formula, solve for y. When you get the two y values, one's positive, one's negative, subtract them and get the length. And then I did it generically, and I came up with a little formula for you. And the little formula is, if I just double the b squared and divide it by a, that's the length of your lattice of each one. And I wrote that up here, 2b squared over a is your length of each of your lattice rectum, of each lattice rectum. And then one other thing, we're jumping into eccentricity. Eccentricity of a circle, pretty easy to remember. What shape is a circle in? A 0. Eccentricity of a circle is 0. Eccentricity of a parabola never changes. It's always 1. But the eccentricity of ellipses and hyperbolas change because their shapes are changing. Like it could be really stretched, really round, right? So what you do to find the eccentricity for both of those is find C, put it over A. So if I know my C and my A, just put C over A, that's your eccentricity. And the closer the eccentricity is to 0, what do you think this ellipse looks like? Closer to a circle. The closer it looks to 1, guess what it starts looking like? It actually ends up looking more like a line, but that would make sense. But it does actually end up looking more very skinny, very linear looking. All right? And then you'll see on the flip side, when we get to hyperbolas, eccentricity ends up being greater than 1 because the C value will be bigger than that A. Are you with me so far? I know I'm dumping a lot on you. We're just going through all this. Oh, and real quickly, do you remember what the area of a circle is? The area of the interior is what? Pi r squared. And isn't the radius like radius? So pi r times r Well, what's that length and that length on a hyperbola?
A and B.
A and B. So the area of an ellipse is pi AB.
Oh.
All right, but that's why it's pi r squared. It's just because your A and your B are the same value if it's a circle. All right, and that's also listed somewhere up here. Yeah, right here. All right, so we'll go back through all those over the next couple days, few days, but I'm just, again, trying to shove everything in your face at this point. All right, so hyperbolas. A lot of similarities with hyperbolas, especially in how you get started. First thing, you look at it, and you're going to have to look at it in this form. So if I give you something like this, you're going to have to complete the square. But how can I look at this right there and go, I know this is a hyperbola? There's one positive, one negative, okay, with the squared terms. It doesn't even matter that the A and the B are different. They could be both 16. If one's positive, one's negative, it's a hyperbola, okay? Now, I do the same thing I did before. Put the x's, put the y's, factor out that lead number, complete the square. Don't forget to add stuff to both sides. Clean it all up. And when I get to here, once again, I'm going to divide by that 400. But in the end, I'll see one's positive, one's negative. If the negative ends up out front, switch them around, okay? Now, remember what I said about A and B on ellipses. What was the big one? What did it have to be called? A. On an ellipse. On a hyperbola, it's not the big one. It's the first one. Now, this one happens to be the A squared is 25, and it is bigger, but it's A not because it's bigger, but because it came first. Okay? So if you're looking at these right here, notice I didn't say anything about A being bigger, right? The A is always the one that comes first. Bigger or smaller, the B is going to be the one that comes second if it's in this form. And then what did I say about the relationship between A, B, and C? Do you remember?
A squared, B squared.
Do you remember I said, like looking at these right here, do you remember I said this? I said, if there was a plus there, I would go C squared equals A squared, opposite sign B squared. That's what I did for what? Ellipses. Well, look, I do the same thing for hyperbolas. C squared equals A squared, opposite sign B squared. And that gives you the same way to think about them as opposed to memorizing one formula for one and one for the other. So just C squared equals that, change the sign that, and that gives you a relationship. Now I can take these two numbers and solve for C pretty quickly. Notice the length of each latus rectum is the same. Notice the formula for eccentricity is the same. Although you'll see here the C values are bigger than the A values. So eccentricity ends up being bigger than 1 on these. The difference of focal radii, there's not a sum of focal radii. Like where you add them, you actually end up subtracting, which is a little harder to see. I'll try to show you that. But notice it's still 2A. Notice C is still your distance from your center to the focus, right? And from the center to the vertices is still A. So a lot of similarities here. Let's take a look. If I had something like this, where's the center? 3, -2. What's the A value? 5. So what's the difference of focal radii? 2A, which would be 10. What's the length of the latus rectum? 2B squared, 32, over A, 5. How do you find C squared? A squared plus B squared. So C would be the square root of that. And I can go that plus that's 41, square root of 41. Okay? And then in terms of, we'll talk about asymptotes in a second. There's a better way to do it than what I just did right there. But anyway, just take a look at this. Right here, I would mark the center right here. That's the center. I would find my C value, and I would go to the right and to the left C. And by the way, how do I know that this thing's opening right and left? Because X comes first. It's kind of like a parabola. If X term comes first, when it's in this form, it's opening this way. If the Y term came first, like you see right here, now notice left and right opening, up and down opening. It would look like that. And you always mark the foci and the vertex based on which direction it's going, whether it's a stretched ellipse or whether it's a hyperbola. So right here, once I get the center, I already decided since X was first, it's going left and right. I go left and right C for the focus right here. So to get to each focus, right here, you can see it. Center to the focus is C, right? That would be out here. That would be C. And then center to the vertex is A. There's another vertex there, A. Right? And then once I get those, I'll show you in a couple seconds how you'd actually graph these. Now, when it comes to graphing them, I'm going to start just like I would with an ellipse. So what number is below the x term? 5. Well, 5 squared, right? So the A value is 5. So I'm going to move left and right 5. So from the center, right here, I'm going to go right 5, left 5. So far, pretend you don't see the blue. And then what's under the y squared term? 16. So the B would be 4. I'm going to go up 4 and down 4. Now, if this was an ellipse, I'd just connect the dots. But it's not an ellipse. It's a hyperbola. So what I do is I create a box out of it. And you can see me mark this box across the top, down the sides, and the bottom. And what is this box useful for? Yes, the corners of the graph are what my asymptotes go through. So now that I have the box marked, I can draw an asymptote there, and I usually make those dotted, and I can draw an asymptote there. Okay? Now, at this point, I just have to decide, well, which way is this going? X came first. So it must be opening this way. So I just go to the edge of my box and mark a point right there and there. And I just eyeball it and sketch the graph. So I'm just going to go, all right, from there, it's got to follow this asymptote. So I'm going to head to the right there and head to the left there. And there's really not any formal way to go about doing that. I mean, just sketch it and try not to be like all cutesy. Like I see some people right here, they get all like, I mean, just try to follow the asymptote, right? If you're doing this, it's so cute, but you're not showing me that you know what an asymptote is, right? So make sure you follow along that asymptote at a decent amount. You with me? And by the way, if your hyperbola ended up being 0 right here, this is a degenerate. Now think about this. This slice right here, this is actually a little off. But if I have a double napped cone, think 2 cones on top of each other, and I make a slice straight through, it's going to chop off this bottom part. So you can see the bottom part of the hyperbola right there. Y'all see that? But you'd also have a top part. Well, that's what a normal hyperbola looks like. A chop straight up and down, top and bottom. What if it was degenerate? What does it have to go through? The tip. What does this look like if I go straight down through the tip? I'm going to split this completely in half. So what does it end up looking like? Just a triangle. And the triangle here on the bottom and the triangle here on the top, when I split a cone perfectly in half, those are the asymptotes of your graph. So the asymptotes of your graph are actually your degenerate ellipse. I mean, a hyperbola, which means it's basically an X. Okay, now, the way you can cheat and do that, one way, which I don't think is the easy way, is to actually take your hyperbola and put a 0 at the end and solve for y. Move the y over. You can see I actually moved it over and then switched sides, but this is changing the y to a positive, moving that over, then changing that to a negative. But you can see that and that. Square root both sides, square root the top and the bottom, but one of them has to have a plus or minus when you square root both sides, so I put it there. And then multiply both sides by a 4. That 4 goes away, and that becomes a plus or minus 4/5. And what do I have there? 2 lines going through the what? The center and a positive and negative slope stand for both. Well, rather than do all of that math, wouldn't it be a little easier just to do this? Okay, I know my center is at -2, 3. Why don't I just, if I want to do this, rather than put a 0 there and do all that math, why don't I just take the y plus 2, take that, and just figure out what the slope would be. And isn't the slope of the box whatever you rise over whatever you run? And isn't that a little easier? Okay, I've thrown a lot at you. Do the best you can on the reviews. We're going to do a big Q&A tomorrow and start really kind of working out some of these issues you might be having.
Did y'all see the band's Instagram post? Like, it was posting about all the alumni, and it said,
They put you for your brother.
they said it had a picture of Caleb, and it said Luke McClendon, NCC LENDON, and with a picture of Caleb. And so he texted him, but they also had the Gaddis brothers, James and Robert Gaddis. They had as James and Robert Merchant. And I had to correct that too.
And they just deleted it and like
Yeah.
posted it again.
Good morning, Homewood High School. Welcome to another day in educational paradise. Please stand for the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Please pause for a moment of silence.
These are the 6 attributes of the homeward spirit. Respect yourself, others, and the environment. Make good choices, even when no one is watching. Celebrate uniqueness. Everyone is different. Words matter. Think before you speak. Seek ways to serve others and be your personal best in all you do.
Excellent. All right, 2 words for today, everyone. The 2 words for today are blood drive. Blood drive. That's right. Our JROTC is hosting Red Cross this Friday. I think many of our students noticed the sign-up in the lunchroom yesterday. We had a great response. So I'm reaching out to you, faculty and staff. Encourage you to give that consideration and step up, sign up. Good luck to our basketball team tonight on the road. Beat Pelham. Go Patriots.
Hey there. It's heartbreaking.
That was a good game, but I was supposed
You what?
to have won that game.
Yeah. They played hard. I was proud of them, but I just saw it coming. I was like, I'm gonna get my heart ripped out. Because I was totally ready for them just to lose badly. And then every quarter you're like, okay, well we played great for a quarter. Now the wheel's gonna come off. 2 quarters, 3 quarters. I mean, when have we ever been winning the game for 59 minutes and 40 seconds? It's like that Florida State game for the national championship where they scored with like 13 seconds left. I knew we weren't going to win in overtime. I mean, we kept matching them. We kept matching them. I'm like, okay, maybe we'll get lucky. But I thought at that point, our quarterback couldn't run. You need a good kicker in overtime. He couldn't kick. I mean, he was good actually, but he wasn't our first kicker. He actually played great. Who knew he would walk in there, kick a 49-yarder? You know? It was a good game either way, but that's the first time we've had a close game with them and lost since 2009. Because every time it's been close, we've pulled it off. I think either one of two things. Either they were really not planning on us being good. Like, I think that they were kind of looking forward to Georgia. Not Nick Saban, but I think those players were like, oh, we'll handle business against Auburn. And then they got smacked in the mouth, and all of a sudden they're spinning, and they're like, uh-oh. And they came out there a little arrogant, but either that or Georgia's going to kill them. You may be right, but if they can barely score on our defense, and our defense was just in shambles. Georgia's defense is the best defense maybe I've ever seen. I mean, they may get throttled. It could totally be 30-something to 10. Because if they can only score 10 on us in the regular period, how are they going to score 10 on Georgia? If you take Georgia's starting defense, I'd be willing to bet at least 9 of them will get drafted. And a good number of them will get taken in not this year, because some of them are freshmen, sophomore, juniors, but maybe all of them get drafted. And in their 2 deep, I bet 14, 15 get drafted. And a lot of those in the first, second, third round. I mean, they're future NFL players all over the place there. And Alabama maybe too, but Alabama's not playing as a team. They don't. And I think a lot of that is you got to look back, even though they're really talented, Alabama lost a ton of players to the draft last year. I mean, they lost tons of people. So I don't know that they've ever really gelled right. And I think they spent a whole year hearing how great they were. They thought they'd just come back and repeat that with their quarterback. But anyway, I was proud of the way the defense played. That quarterback, he's not very good, but I was proud of him he played with a sprained ankle and yeah, I mean it didn't look good.
I thought he was gonna be terrible than that.
Yeah, I did too. But for a guy who couldn't even move, he fought. I was proud of him too. Oof.
But when they go to a little ball,
They might. I've heard the rumblings. I've heard is either the bowl in Nashville or here. because Alabama has that Birmingham Bowl, and it would be actually a fun game to go to. It'd probably be played in that new stadium.
Man, I even go to that.
I probably would go.
I would go.
Yeah.
Let me know if you need anything about.
Okay. Yeah. Sure.
Have a good day.
You too.